Hello everyone, Namaskar. Today in this lecture we will discuss about control atmosphere storage. We will discuss what is the control atmosphere storage, various design aspects of a CA chamber, how we control the gaseous composition in a control atmosphere chamber like O2, CO2, ethylene etc. and also the different sensors which are used in CAS unit we will also discuss. Then in the towards the end of the lecture we will take up a few case studies on control atmosphere storage of fruits and vegetables. You know, in CO storage the oxygen and carbon dioxide levels are continuously maintained different from the ambient air. So, it is a chamber enclosed chamber where by artificial means, by mechanical means or by other suitable means O2 and CO2 levels are maintained, which are required for the particular commodity that is to be stored in that. Generally O2 level is brought down and CO2 level is raised, and here again like in the earlier lectures we have discussed about active packaging, modified atmosphere storage, edible coating etc. So, this is also a method of shelf life extension of the commodities by controlling the rate of respiration. So, by maintaining low level oxygen level and high carbon dioxide level, we try to regulate the respiration process of the commodity. Okay. And of course, these are the high end technologies are used here to adjust the O2 and CO2 levels to the predetermined set value for getting maximum shelf life, maximum advantage as far as the product is concerned. So, there are two types of CA chambers which are commonly used. One is the Polyflex unit and the other is the air or gas tight chambers. In the Polyflex unit, it contains, you can see here in the figure, it contains a special plastic pallet or several plastic pallets. There is a plastic cover for gas tight sealing. There are bottles of nitrogen for oxygen reduction, bottles of CO2, gas inlet and outlet holes, and a fully automatic measuring and regulating system with a built in O2 CO2 meter. Okay. So, in this pellets, plastic pellets, the composition of gases is maintained. So, advantage of this system, that is the major advantage is that you can maintain different gas conditions in a pellet, and in a storage facility several pellets of this type can be kept. So, therefore, in the same storage chamber various gaseous composition, that is each in one pellet, can be maintained. Okay. In the gas tight storage chamber, that is a here, that is a whole room facility is there, and where all the instrumentation and control instruments etc., that is which are required for bringing down, first regulating the O2 and CO2 level, and that is the controlling O2 and CO2 level, and then maintaining it at a proper level. So, the capacity of the storage cell chamber depends upon the total tonnage of the fruit or vegetable which is to be stored inside the room, bulk density of the fruit or vegetable or commodity, volume of storage accessories, free volume inside storage facility required for material handling. So, in a commercial control atmospheric storage room, it is recommended that 65% of the total volume should be kept free for easy movement of gases etc., and it helps in maintaining the proper gaseous composition. So, total volume required V will be BSA plus BF plus FV, where VSA is the volume occupied by the storage accessories, VF is the volume occupied by fruit, which is you can find out that is by weight of the fruit if you know. So, weight of the fruit divided by density of the fruit or density of the produce, weight of the produce divided by density of the produce is the volume occupied by the produce, and then FV is the recommended free volume, that is 65% or you can say 0.65 V. Then let us discuss about design of a refrigeration unit. Okay. The heat load added by the product to be stored in the unit is important in deciding the refrigeration capacity of a CA storage unit. There are various types of load like transmission load, infiltration load, product load, respiration load, internal load or defrost load, etc. But three major loads which are considered in designing the refrigeration unit include chilling load, heat of respiration and heat conducted through the storage unit. Okay. Let us see chilling load. This chilling load QC, it considers the amount of heat required to be removed from the product. QC is equal to MCP T1 minus T2 by T, where M is the mass of the product, Cp is the mean specific heat of product and T1 minus T2 is the initial and final temperature difference, and small t is the chilling time. Heat of respiration, you know the commodity when it is kept inside the storage facility, then it continue to respire and it will be good till it is continuing respiration aerobically. Okay. So, the commodity takes oxygen, okay, and inside the sugars etc. carbohydrate they are oxidized, and carbon dioxide gas and energy and water, all these things are released. Earlier we have seen what is the respiration equations and all those things. So, the amount of heat generated by the produce, that is during the respiration process, is calculated as QR is equal to mHg by T. Okay. That is where m is the mass of the commodity or food and Hg is the heat generated by food and T is the time. So, by if you know that how much commodity, how much produce is stored inside the storage environment, okay, and what is the heat generated by it at time, then heat of respiration can be calculated. Okay. Then heat conducted through storage valves, another important factor, that is the steady state heat flow by conduction from the valves and ceiling is calculated based on Fourier's law of heat transfer, that is Q is equal to U A delta T, where A is the area perpendicular to the direction of heat transfer, delta T is the temperature difference between inside and outside the chamber, U is the overall heat transfer coefficient, it is calculated based on the insulation and wall thickness, that is delta x. 1 by U is equal to 1 by H0 plus dxin by Kin plus dxw by Kw plus 1 by Hi, where Kw and Kin are the thermal conductivity of the wall and the insulation, and Ho and Hi are the outside and inside convective heat transfer coefficient. So, from this one can calculate the heat conducted through the storage valves. Then let us discuss about how to control oxygen in a CA chamber. Okay. The concentration of oxygen can be decreased by purging the inert gas. Normally the nitrogen is used and nitrogen is purged inside the storage chamber, and by this oxygen amount is controlled, because in the atmosphere always combination of water, that oxygen, carbon dioxide and nitrogen level is fixed. So, if you increase the level of nitrogen, so obviously oxygen level can be brought down. Okay. So, nitrogen is separated from air in a nitrogen generator. Okay. Pressure swing absorption system technology is used to separate nitrogen from the components of air, that is mixture of O2, CO2, water vapor, etc. So, the separation of nitrogen takes place in an absorber vessel filled with carbon molecular sieve. Okay. So, the operating principle of the nitrogen generator is shown here, that the separation of N2 from air takes place due to the faster kinetic diffusion of oxygen molecule into the pore structure of the carbon molecular sieve, okay, which is known as CMS commonly. Then that is an O2 nitrogen molecule, that is the oxygen diffuses at a faster rate than the N2 molecule, because O2 molecule is smaller than N2 molecule. So, you see that here, that in this schematic is shown, where CMS absorbs O2, CO2, moisture in compressed air in a short period of time, and compressed nitrogen gas is available at the outlet. Okay. Okay. Then when the pressure decreased to the atmospheric or vacuum level, the CMS, which has absorbed O2 gas and others, easily absorbs them and is regenerated. Okay. You see, that is the compressed air, that is air intake is the compressed air going, it is the CMS columns air in the picture. You see that air goes and then nitrogen is purging here. So, finally, that oxygen goes out and this nitrogen is remained, and oxygen goes out, and the amount of oxygen inside the storage chamber by this purging is reduced. Okay. The nitrogen generation, in fact, the adsorption and regeneration operations are done alternatively between two adsorption columns, and nitrogen gas can be made available continuously from the air. See, that is the red color, the compressed air is going, this is absorber A and then absorber B, and through this, right? So, it absorbs that and the water gas and other things, it is left to the atmosphere, and this green line finally it goes to the, that is the nitrogen. Okay. And this nitrogen is continuously comes into the storage environment. So, one can calculate the capacity of the nitrogen generator required in the storage facility for maintaining proper O2 level. Okay. So, the volume flow rate of nitrogen in the CA chamber depends on mainly oxygen concentration set point in the CA chamber, that is what is the level of oxygen which you want to be controlled, and then free volume of the CA storage. So, to develop relationship between the amount of nitrogen required and the different operating parameters of the CA chamber, it is assumed that the chamber is leak proof and perfectly well mixed, that is all the insulation etc., they are working properly, there is no leakage of gas. Then also another assumption is that the change in gas composition due to respiratory metabolism of stored produce during nitrogen flushing is negligible, and concentration of oxygen present in nitrogen is the same throughout the flushing period. So, these are the important assumptions, and based on this the capacity of the nitrogen generator is decided. So, first thing is that mass balance between the inflow of oxygen and outflow of oxygen in the CA chamber is done. So, how it is done, that you can see these equations, that is moles of O2 inflow becomes Vn2 into O2n multiplied by rho O2 into dt by MO2, where the moles of O2 outflow is Vn2 multiplied by O2t multiplied by rho O2 multiplied by dt by MO2, where Vn2 is the flow rate of nitrogen gas, O2n is the concentration of oxygen present in nitrogen, that is the percentage, O2t is the concentration of oxygen present in the CA chamber at time t, that is t is the flushing time in seconds, and MO2 is the molecular weight of oxygen, and rho O2 is the density of the. Then combining these two equations, that is the inflow and outflow mass balance equations, total moles of oxygen accumulation can be found out, that is equal to O2t minus O2n multiplied by Vn2 multiplied by rho O2 multiplied by dt by MO2. So, this is another equation third. Okay. Also, we can estimate the volume flow rate of nitrogen in the CA chamber, and for this total moles of O2 accumulated in the CA chamber during the flushing time T is calculated by minus Vf multiplied by dO2 T into rho O2 by MO2. So, that is equation 4. So, if you combine the earlier equation 3 and equation 4, it gives the total volume flow rate of nitrogen, that is Bn2 in the CA chamber. So, one can solve these equation 3 and 4 and finally get the equation, that is Vn2 is equal to Bf by T multiplied by ln O2A minus O2n divided by O2T minus O2n, where Vf is the free volume in the storage capacity, T is the flushing time, O2A is the oxygen concentration in ambient air, O2n is the oxygen concentration in nitrogen gas, O2T is the oxygen concentration in the storage facility at any time T. Then another important aspect which is done is the humidity control. Okay. The moisture loss of stored product inside the CA chamber reduces if the relative humidity levels are kept above 90%. So, it is required in order to make sure that the commodity in the storage environment is not dried, not shriveled, etc. Relative humidity also is maintained at proper level. So, for this a humidification system is generally used in the CA storage facility, okay, which maintains the relative humidity up to the desired level. So, the relative humidity in the storage facility can be controlled by the fine water spray or steam, that is here that mist fine water spray, that is the disc circulates and through these holes the water is. So, if you want to increase the humidity or if you want to decrease the humidity accordingly either water spray or steam spray is done. So, one can calculate the capacity, the determination of the capacity of the humidifier depending upon the room size, etc., what is the commodity, how much you want to have the humidity level. So, one can find out the what should be the capacity of the humidifier, that is the final capacity inside the CA chamber is determined based on the principle of mass and energy balance, here simple equations. So, let us have the, that is if the flow rate, humidity ratio and enthalpy of the initial air stream in the CA chamber be M1 H1 and capital H1, saturated air stream from the humidifier be M2 S2 and capital S2, and finally, the desired air stream in the CA chamber be M2 S3 and final capital S3, that is. Then the mass balance is done by balancing the air flow rate, that is M3 is equal to M1 plus M2. Okay. And humidity ratio in the CA chamber is determined by the humidity balance equation, that is M3 S3 is equal to M1 H1 plus M2 S2, and enthalpy of the air stream in the CA chamber can be determined by the energy balance equation M3 S3 is equal to M1 H1 plus M2 S2. So, by solving these equations, that is the mass balance, humidity balance and enthalpy balance, one can determine the mass flow rate of the water jet in the CA chamber for the desired humidity control. Then another important aspect is the carbon dioxide control in the CA facility. We discussed about oxygen control, which is done by nitrogen purging, then humidity control, and now important aspect is the carbon dioxide control. So, you know that the air contains about 0.03% carbon dioxide. So, target value of the CO2 set in the CA chamber is usually greater than that, sometime maybe 5% and in some specific capacity specific product are even little more than that sometime. So, that one can find out that rate of the CO2 accumulation in the CA chamber due to product respiration, because when the product you have kept, it is respiring and because of that CO2 product is evolving, giving out the CO2. So, it is accumulated in that. So, that CO2 accumulated in cc per hour is equal to mass of the stored product multiplied by rate of the carbon dioxide production per kg of the product. So, by this you can find out as what will be the amount of CO2 that will be accumulated in the storage facility due to respiration. Then rate of the, accordingly you can find out rate of the CO2 inflow in the CA chamber from the cylinder, okay, and that is the CO2 required is target value of CO2 set, that is how much you want to be controlled in the storage room, minus 0.03 divided by 100 and whole thing multiplied by free volume inside the CA chamber. Okay. So, that is the CO2 required inside the chamber. Okay. So, if CO2 required is greater than CO2 accumulated, then the carbon dioxide gas is purged in the CA facility from CO2 cylinders, and vice versa, if CO2 accumulated is greater than CO2 required or CO2 required is less than the CO2 accumulated inside, then CO2 level inside the control atmosphere facility is maintained by using CO2 scrubbers, because in that case you have to remove some carbon dioxide. So, one can use scrubbers, etc. So, air from the storage area is removed by the CO2 scrubber and the CO2 purifier is then fed back in. The CO2 scrubbers has a cycle of two activities, that is absorption, that is removal of CO2 by using active carbon filter, or regeneration, which does cleaning of the active carbon filter. So, by this way one can maintain carbon dioxide level, regulate it and control it and then maintain it at this level. Then ethylene control, another important, that is in the storage facility, whether you want to delay the respiration or delay the ripening or hasten the ripening, etc. Accordingly, ethylene control also sometimes is needed, because ethylene is the ripening hormone. So, ethyl gas may be added in the CA storage environments to introduce ripening, and that one can calculate here, that is the ethylene required is the amount of ethylene to be maintained in the CO chamber percent divided by 100 multiplied by free volume inside the CA chamber. So, ethylene decomposers remove it from cold storage based on catalytic combustion. The CO2 decomposer uses oxygen to combust ethylene from the carbon dioxide and water, and this enables C2H4, that is ethylene, to be kept at the required level, either ppm level or ppb level, what is desired. So, one can maintain, if you want to delay the ripening, maintain the CO2 as a ethylene as a lower level, or even sometimes ethylene scrubbers, etc. are used. Okay. Or if you want to maintain this fast rate of the ripening, you want to commodity to ripen fast, then one can have ethylene cylinder. With the help of ethylene cylinder, calculated amount of ripening ethylene can be introduced into the chamber. Okay. So, the capacity of the ethylene decomposer can be estimated based on the equation like F is equal to R into M divided by C into D, where M is the total tonnage of the fruit, R is the ethylene production of the fruit, C is the required ethylene concentration, and D is the efficiency ratio, which is a standard. Normally it is the 95% is calculated as the efficiency ratio. So, from this question you can find out that yes, what should be the capacity of the F, that output of the compressor, okay, that is for the controlling the ethylene. Then these are the gaseous composition. Now, for monitoring, for seeing, just evaluating, seeing that whether this really this it is a particular level of gas composition, O2, CO2, N2, etc. is maintained or not, various sensors are used. Okay. So, for oxygen sensors, generally zirconia sensors are used for the measurement of oxygen. Zirconia ceramic cells only allow oxygen ion to pass through at high temperatures. As you can see here, that is these are the near sensor, that is oxygen is coming and going, that is current output and sensing voltage etc. So, in the sensor it passes with reference gas on one side and the sample gas on the other side. The oxygen ions move from one side to other side with the highest concentration to the that within the lowest concentration. So, the movement of ions generate an electromotive force which can be measured to determine the oxygen content. Then carbon dioxide sensor, when a light source is exposed to a gas stream containing carbon dioxide, energy from the infrared region of the spectrum is absorbed by the gas. Okay. And the amount of light absorbed by the gas stream is directly proportional to the CO2 content in the gas stream, and that here infrared light is there. So, by this one can, there is a detector which detects the carbon dioxide and then it indicates. Then ethylene sensors, that is silicon carbide based gas sensor is normally used for ethylene detectors. Okay. How it works? It is shown here in the schematic of the figure. There is a ethylene gas chambers, okay, that is the reducing valves, and it comes here. There is a flow container here, and then it is connected with a ethylene monitoring device. So, the sensors is calibrated, it senses this and then displays in the monitor. Okay. Now, finally, the factors affecting the quality of the stored products. Okay. As you know, earlier also we have discussed, okay, that if the carbon dioxide level increases in the storage facility, then oxygen consumption rate maybe will be decreasing, and the acetaldehyde production or ethanol production will be, that is means that is the anaerobic respiration will more the higher the carbon dioxide, higher will be the anaerobic respiration rate. If the here is the effect of O2 level on respiratory, that as the O2 level is increasing, then means aerobic respiration is continuing at a longer rate, and then anaerobic respiration rate decreasing. So, this is a general thing earlier also. So, particularly that is the various factors which influence the quality of the stored product inside the CA facility include species of the crop, cultivar variety, concentration of gases which are stored in the facility, crop temperature, degree of ripeness of the climatic fruits, state of maturity of the crop at harvest, growing conditions before harvest, or presence of ethylene in the store. Okay. The advantages of a CA storage means a considerable decrease in the respiration rate with a reduction in the climatic maximum is accompanied by an expansion of both the pre-climatic and post-climatic periods. So, there is a reduction in the effect of ethylene on metabolism due to the interaction of O2 with ethylene, with a consequence delay of appearance of senescence systems. Okay. And therefore, it results in the extension of shelf life. The preservation of an excellent firmness of the flesh due to the effect of CO2 concentration on the enzymes acting on the cellular membrane is there, like the firmness of the flesh is maintained. Okay. Also, a high turbidity is achieved such that the fruit are more juicy and crisp. A smaller loss of acidity, sugars and vitamin C is observed there, that is so that the nutritional and sensory quality in the CA storage fruit is higher. A limited degradation of chlorophyll, and also the color of the commodity becomes stable, it is stabilized and its green color is retained when it is the commodity is kept in the CA facility. Even some physiological alteration such as chili injuries, spot decay, browning, water core, scales are even they are also prevented or greatly limited depending upon the conditions that are maintained. Molds can be reduced their growth in particular under low oxygen and high carbon dioxide atmospheres. So, here in this table various levels of threshold levels of oxygen or carbon dioxide required to cause injury to some fruits and vegetable is given. Okay. For example, you see that is the apricot, that is the CO2 injury level is maximum is the 5%, and if that is the CO2 level goes above 5%, then there will be loss of flavor, flesh browning, etc. Similarly, the oxygen injury level means less than 1%. So, oxygen has to be at least 1%, more than 1%. If it goes less than 1%, there will be off flavor development, etc. In banana, the CO2 level is more than 7 and O2 level is minimum less than 1. Similarly, in cabbage, more than CO2 injury level is more than 10 and O2 injury level is less than 2%. In mango, CO2 injury level is 10%, maximum 10%, and O2 injury level is minimum less than 2%. So, for tomatoes, more than 2% for mature green and more than 5% for turning tomatoes, okay, and that is the CO2 injury level, whereas less than 2% is the O2 injury level depending upon the length of exposure. And what are the injury, that is the CO2 injury symptoms and O2 injury symptoms, they are described here in this table. Okay. Here you can see some case studies of the selected fruits, all right. In the stored are the control atmosphere storage, like even 6 months storage of Bartlett pears. You can see this is the 30° Fahrenheit, that is -1 degree Celsius in ambient air, and then -1 degree Celsius in 2% oxygen environment, and you can see the difference. Similarly, here that tomato, that is low O2, retards ripening of partially ripe tomato fruits. Here oxygen concentration is maintained less, so it remains green for longer time, okay, and in the control it becomes ripes early. Here in the apples, that is the reduces chilling injury of avocado with control atmosphere. You can see that level of 2% O2 or 2.5% CO2, that is and less than 1.01% ppm. Okay, that is how this chilling injury is removed. You can see here in the picture. Similarly, in the pomegranate, okay, it enhances the shelf life under the control atmosphere storage, 5% O2 and 15% CO2 in this case. After 3.5 months of storage, you can see how it looks like, and in the air, that is, so it's better maintained. Even in the case of potato, there are certain reports that low oxygen stimulates sprouting and increases the decay, that 0.2% O2. So, you see 2% O2 here, that sprouting is seen, whereas the 25 degree Celsius in air normal atmospheric air, that is the decay is not there. Okay. Then similarly, low O2 injury in the apple, you can see here, or CO2 injury to apple fruit, that is at different level O2 and CO2. So, there are similarly many such reports and many such researchers has been done. So, this is here a pilot scale CAMA storage facility, which we have developed and got it fabricated, and it is installed in our department, okay, in our department premises. And in the chamber, it has got 4 chambers, and each chamber has got the storage facility of, as you can see, that is 1, 2, 3, 4 chambers, and in each chambers 250 kg of fruits and vegetables can be. So, finally, overall 1000 kg storage capacity is there, and its unique feature are that each of the chamber is independently controlled. Okay, each chamber can be individually opened and closed. Okay, it can be centrally monitored also, the central control is there. Okay, and that is individual chambers are PLC control, as well as central PLC control is there, and also there is automatic record keeping in this computer, it is there. So, the features are that is temperature from 0 to 50 degree Celsius, it can be controlled any range, and oxygen from 0.1 to 25%, CO2 from 0.1 to 25%, and relative humidity from 10 to 95%, and ethylene from 1 to 1000 ppm. So, in this range, any either this a condition in all the chambers or in individual chambers, it can be maintained, whether you want to delay the rate of ripening, whether you want to advance the ripening or you want to extend the shelf life, accordingly the condition can be maintained. and this is a just a container, and if that some engine it is provided to it, it can be even movable container. So, with this I will summarize this lecture that yes, CA storage is a very important and useful technology, particularly for the storage of perishable commodities. That is since beginning, that is the traditionally we have been using cold storage facility, cold store for the storage of perishable commodities, particularly fruits, vegetables, etc. Because when you are lowering down the temperature, the rate of respiration is lower down. But now it has been proved that along with the temperature control, if composition of the gaseous composition in the inside the storage facility is control, you will get added advantage. So, suppose you are keeping a commodity in a controlled atmosphere storage or in a normal is in a atmosphere storage, cold storage where the only temperature is controlled. Okay. Let us say that yes, temperature is controlled at 5 degrees Celsius in the and a particular commodity you are getting X shelf life, X month or X days, and in this in the same facility along with the temperature, if you also regulate and maintain the O2 CO2 level in the storage facility, depending upon the commodity that has been stored there, you will get Y shelf life, and Y is always higher than X. So, that is here the beauty and advantage of. So, now in fact, it is being encouraged that almost most of the CA storage, that is the cold storage unit, they should be converted into the control atmosphere storage unit. So, you have the temperature control, along with that O2 control, CO2 control, etc. should also be humidity control. So, if all these things are properly controlled and maintained at desired level, you will get. So, there may be some additional cost involved in this converting to cold storage, traditional cold storage into control atmosphere storage, but the quality which you get, the extension of shelf life which you get, that in the long run is going to be a advantageous process, and also it will be an economically viable process. So, this I conclude this lecture. These are the references. Thank you very much for your patience hearing. Thank you.